See, if I'm coming in along that diagonal, then every y value is actually the same as the x value, so I can replace the y's with x's. You could have equivalently replaced all the y's, all the x's with y's, right? It would have been the same thing. Let's algebraically clean this up and see what we get. Limit x approaches 0, 0. We get x squared on top, and on the bottom we get 2x squared, don't we? And then the x squareds go away, right? And you just get 1/2. And guess what? That's not 0, right? The other two paths were 0, and this path is 1/2, which means I've shown now that this limit in general, right? This limit in general does not exist, right? It does not exist. Yes?
So, question, moving off of what you said a second ago about analyzing and seeing based on the equation that it could, is that ever a possibility?
Is whatever a possibility.
That you could analyze an equation and see that all possible answers will come to the same answer?
I wouldn't trust my analyzing for that.
Okay.
Yeah, I would be too afraid that there's a path I haven't considered.
Okay.
And so I'm going to give you a really good example in a second where nobody here would have come up with the path. Like we can come to a conclusion. All right, so can we look at the picture of that? This is the surface. This is the surface we're talking about. This is actually a different surface than the one we looked at a second ago. All right, this is the problem that we're looking at that we just finished. That's the surface. And we said that if we came in along the x-axis, that the answer was 0. So let me pull out let me come in from the side. Can y'all tell that no matter where you come in along the x-axis, that the z coordinate's always 0? Mm-hmm. You know, does y'all see it there? And then if I come in along the y-axis, same thing. As I'm moving along the y-axis, my surface is actually, as I approach that point, the z coordinate is 0 as well. But if I come in along the diagonal, let me pull that out. Y'all see that diagonal on the domain there on the bottom? As I come in along the diagonal, do you see that we're actually up now? We're up 1/2 as we approach that origin. So I hope that visual makes some sort of sense, that you can tie it all together. Yes?
Are you able to replace y with like whatever
Anything.
like sine of x?
Yes. You can do anything you want, right? That would be any path. So what's being asked is, like, if we just came in along y equals x, right? But what if I wanted to approach the origin along the sine function, right? Then what I would do is I would use this curve y equals sine x. And that means I would go in, I would rewrite my limit, and everywhere I see y, I'd replace it with sine x. And then I'd do that, and whatever happens, happens, right? That's not going to happen in this class. We're not going to do that, but I'm just saying, like, we could do that in theory. All right, this one. I'll write it so you can see it a little bigger here. Limit xy approaches 0, 0 of xy squared over x squared plus y to the 4th. Yeah, this one's, you don't have that symmetry anymore. It's somewhat symmetric, but not symmetric enough, all right? Let's see what happens. Shall we stick to the convention? Let's come in along the x-axis and then the y-axis. Try that. Okay, first along the x-axis. So I'm going to replace all my y's with zeros. Replace all my y's with zeros. Limit as x0 approaches 0, 0 of, let me just write it down, 0 over x squared plus 0. Right? If I replace y with 0 here, it kills off the whole top. And if I replace that y with 0, it's a 0 there. And that answer is 0. Any questions on why I'm getting 0 there? We get 0 over x squared, right? 0 over x squared is going to be 0. Let's try along the y-axis. So x is going to be 0 here. And if I do that, I believe we get the same result. Right? 0 over, well, the same answer. It doesn't look exactly the same, but we get that instead. We get 0 over 0 plus y to the 4th. And because the top is exactly the number 0, we get 0. So far, this is not good, right? We need to come in along a different path, right? So the diagonal seems like the next natural choice. Yeah. I'm going to do something even better than the diagonal. Even better. I'm going to pick, not the diagonal, I'm going to pick a line, and it's going to be arbitrary, which means that I'm going to say not y equals x, but y equals mx. Because m is the slope of the line, right? And plus nothing means the y-intercept is 0, which means this line goes through the origin, right? And as I change the value of m, it's just going to turn and change the slope of the line, right? So by doing this, what I'm going to do is I'm going to check all possible lines at one time. All possible lines that go through the origin. I'm going to check them all at the same time, which is pretty awesome if you think about what we're about to do, all right? So let's do it. I'm going to come in along the path y equals mx. And then that means I'm going to be replacing y with mx, right? Y is going to get replaced with mx in this limit. I'm going to write it over here so I have a little more room. Limit, I'm going to go x, mx approaches 0, 0. And then I'm going to have x, mx squared over x squared plus mx to the 4th power. Do y'all see I've just replaced all the y's with mx's? And now I'm just going to clean this up algebraically, see what I get. So this equals the limit as x mx approaches 0, 0. On top, when I square this, I square the m and the x, and then I hit it with that x that's in front. So I get m squared x cubed over, and on the bottom, I get x squared plus m to the 4th, x to the 4th, right? Just raising both those factors to the 4th power. And I'm going to try here in a second. I'm not going to do it yet, but the idea is that I'm going to be letting x go to 0, right? If x goes to 0, then mx goes to 0 as well, right? They both go together. So right now, if I do x goes to 0 right now, I get 0 over 0, and that's, we don't know, right? So the reason previously, right, that we could say the answer was 0 is because the top was the number 0. Here, it's not. That's not the case, right? It's approaching 0. But I can do something very, very easy algebraically. Yes?
Factor out x.
Yeah, factor out x squared. And then just reduce everything. Let's just reduce everything by 2 factors of x, right? How do you want to? I'll do it in different colors. So basically what I'm doing is I'm taking this, I'm pulling an x squared out of the bottom. I get 1 plus m to the 4th x squared, right? That's what the bottom would become. And then when I reduce this and that, I will get this new limit. I'm going to rewrite it so we all see it. Limit, we're letting x mx approach 0, 0. And on top we have still m squared x. And on the bottom we now have 1 plus m to the 4th x squared. And if I take this limit, I do not get 0 over 0 anymore, right? I get 0 on top, right? X is going to 0, so that's 0. And then this right here is 0, but we still have plus 1. So we get 0 over 1, which is 0. Who has a question? Have we gained any ground here at all? Yes?
If you square root of x, y equals square root of x.
You want to try y equals the square root of x? Okay, I'm going to do it just because. Let's see what happens. All right? Y equals the square root of x. This is the chosen path here. Right now, though, we don't know anything, right? From the x-axis, y-axis, and then from an arbitrary line, they all gave us the same limit of 0. Yes?
So if m equals any number other than 0, then it has multiple possibilities?
So if m is some number other than 0, let's just say, then do you agree that that has no impact on the fact that this is going to go to 0? Like, you just give me a number m, whatever, 10, 100, 1,000,000, 4, give me any number. I'll plug it in here, I'll plug it in here, and then it doesn't matter because as x goes to 0, it's going to kill that off and leave me with 0 over 1. So what we're saying is, when you look at these lines, right, these lines that I had, the mx could be any of those lines, right? As long as m wasn't 0, right? As long as m wasn't 0. But if m is 0, we're talking about the x-axis, which we've covered, haven't we? And if m is, well, what about the vertical line? Well, that's the y-axis, right? Vertical lines don't have slopes. So we've covered every possibility here, right? We've covered when m is any number, when m is 0, and if m, well, it's undefined. If the line is vertical, then it's the y-axis. We've got that covered as well. All of those answers give us 0. Okay, yes? That good? Yeah, go ahead.
So the three possibilities that you should always check is the x, the y, and then the x.
Yeah, that would be a good starting place. That would be a good starting place. Check the x-axis, check the y-axis, and then if that doesn't work, try mx. If you do that, then what you've done is you've checked every straight line path to the origin. You've checked them all. If those don't work and you get the same answer for each one, then we've got to try a different path that's non-linear. So the suggestion here from Ian is to do what did you say?
Y equals x squared.
Y equals x squared, or
Y equals square root of x.
y equals square root of x. Yes?
Question. Wouldn't checking y equals mx, couldn't you just start with that because that would automatically check your x and y intercept?
Sure, it could. It could. Now, it'll only check your x-axis, because your y-axis is a vertical line, and y equals mx can never be vertical, right? So if you want to like really break it down, you could do y equals mx, and then you could do the y-axis. Instead of x-axis, y-axis, y equals mx. All right, so the suggestion here is to come in through this path right here, along this path. You said y is the square root of x? Okay, now I'm not going to ask you why you chose that yet. Let's see if this works. We're going to try and come in along this path towards the origin. Let's see what happens. So I'm going to replace every y with the square root of x. Limit x root x goes to 0, 0. And then x, and then square root of x, but that gets squared. And then over x squared plus the square root of x, but that gets raised to the 4th power. This is the limit as x root x goes to 0, 0 of, all right, when we square that, the root goes away, we just get x, so x times x is x squared on top. And on the bottom we have x squared plus, and then the root of x times itself 4 times gives you x squared as well. So you've got x squared, and you add these two together, you get 2x squared, and then when you reduce this, it's going to be 1/2. And it works. Well, it works in the sense that we got something other than 0 now, didn't we? So did you pick the square root of x because you were kind of trying to see what you could do to make it not be, yeah. So you just kind of messed with it, right? It's hard to actually teach that part because you have to analyze it enough to figure out what you're going to do in here that's going to make it actually turn out to be something other than like 0 over 0, right? I don't believe that's the only thing we could have done. Let me see. Let me look at my notes. Let's look at the actual surface, because I think it's really worth us seeing this surface. It's really kind of cool looking. Here's the surface, right? It's really, really kind of nice, isn't it? Do y'all see those parabolas? Do y'all see those little parabolas in there? Okay, so when we approached along the x-axis, we were always, no matter where we were always down at 0. Do y'all see that point down on the bottom? It's basically it's sitting along the xy plane the whole time. If we came in along the y-axis, I don't see the point. Where is it? Where's the point? Oh, there it is. It's hard to see it there. There's the point. We move along there. We are still sitting there on the ground. You can see it from the side there, kind of along the ground. And then if we try MX, this one is pretty badass. I'm proud of myself for the code on this one. Okay, so look at this one. There's our surface, and I'm going to pull the surface out, and that way you can see my diagonal line. That's y equals x. Notice that if I turn it just to the side, can you all see that from the left and from the right we're approaching 0? Okay, now I'm going to change that line. I think it's this one. Whoa, shit. It's hard to see what I just did. Try it again. I'm spinning that line. See how I'm spinning that line around? That's me changing the value of m. And no matter what m I pick, you just tell me where to stop. Stop there? Fine. Now let's look at it. Do you all see that? Again, from both directions, we're approaching 0. Right? That's visual verification that it doesn't matter which line we come into 0, 0 with, it doesn't work. Now, we used y is the square root of x, right? Which is the same as this if you just take the square root on both sides and only take the positive case. And do you all see that that's a parabola. Do you all see if we move along the parabola, we're not down on the ground? It keeps us up on that top edge of that surface, and so we're not down below. So that's the way. And you can see we're up at 1/2 the whole time. Okay, so that's it. On your homework problems, I do not recall a problem where you're going to have to extract something crazy, all right? It's mostly you're going to do like x-axis, y-axis, maybe y equals mx, and you're going to get differences and you'll move on. So it's not going to be nuts. It's really just making sure you understand the fundamental principle of this. All right, so that answer was it doesn't exist. Now, there is really one way, and one way only, to show that a limit of a function of two variables does exist, and that is to use the squeeze theorem. So if you recall the squeeze theorem from Cal 1, great. If you don't, I'm not going to run through the whole thing in detail, but I'm going to work through this example. And when I work through this example, hopefully the idea will make sense of squeeze theorem. So what I'm going to do here is this. I'm going to take the function right here. I'm trying to figure out what happens as we go to 0, 0. Can we just verify right now that when we try and plug 0 into this for x and y that we do get 0, 0? Right? So it's undefined. So we try and check all these paths. I'm going to try something different. What I'm going to do is I'm going to write down the function. And I'm going to try and set up a string of inequalities where I can somehow squeeze this function between two other functions. And then I'll take a limit and see if I can get the two limits on the outside functions to go to the same place. And if they do, then it squeezes this one in between. Let me do it first, and if you haven't seen it, then maybe it'll make sense after I finish it. All right, is there something I know that this is bigger than or equal to? Well, everything up top is squared, so that's got to be a positive number, right? Or at worst, 0. And on the bottom, everything is squared and added together, so that, I'm going to have a positive number on the bottom, but possibly I could have 0, right? But I'm never going to get negatives out of this, am I? So what I can say is this. This is definitely greater than or equal to 0. All right, for sure? All right. Let me give you kind of a preview of where I'm headed on the next step. I'm still going to leave this here for the moment. What I'm going to do on the next step is I'm going to say, hey, I'm going to take the limit as xy goes to the point 0, 0 of this left side, left part of the inequality. Whatever that limit is, has to be less than or equal to the limit as xy goes to 0, 0 of this piece, x squared sine squared y over x squared plus 2y squared, right? If this is 0 and this is this function, then whatever the limit is for this function must be bigger than the limit for this one. And so I need to figure out over here, what do I put here so that I can put like an upper bound on what this limit is. And I'm really hoping to find something here that when I do this limit, that this goes to 0. Because then this goes to 0 because it's a constant, right? The limit of a constant is the constant. So if this side is 0, if I can somehow figure out something to put here that when I take its limit I get 0, then that forces the limit that we're looking for to be between 0 and 0, which means it can only be 0. So I've squeezed the thing we're interested in between two things. Does that kind of make sense to y'all? Like those of you who've seen squeeze theorem a little bit? The question is what though? What goes here that when I take the limit, you know, that's a hard thing to just see right away. So I'm gonna help us see it by moving to the side over here. I'm gonna be off camera for this. Well, I'll try and stay on camera I'll come back here. All right, I'm just gonna take a look at this. Okay, I need to see something that's bigger than this, that I know when I take its limit, it's gonna go to 0. So I'm gonna just tell you what it is first, and then let's talk about why it's this. Do you all agree that that's less than or equal to sine squared y? Think about it, and if you think you know why, then maybe I'll ask you to explain. But if you think you know, show me your hand. Okay. You want to tell me? Since redeem yourself. Okay, so I think, yes, you're on the right track. So what you're saying is that on this side over here, the sine squared y is actually being divided by this, right? And that number is bigger than 1? It is, for sure? Most of the time. All the time? Most of the time? All the time? What do y'all think? Is this number always bigger than 1? Always? Okay, what if y is 0 and x is 1/2? Then it's not, right? You're on the right track, but you cannot tell me that this is always bigger than 1. Do y'all understand that if this was bigger than 1, if it was, then this would be true, because if this denominator is bigger than 1, and over here the denominator is 1, right? I'm ignoring the x squared right now. If you just look at that, if this was bigger than 1, this would be true, right? Because you're dividing by a bigger number than over there. So this ratio should be smaller than that one. So close but not quite, right? Who else? Who else?
My thought is not fully formed, but the sign will just keep, it's bounded.
Which one? What?
The sign is bounded.
This sign is bounded. Well, we could say it's bounded. It's definitely less than or equal to 1, isn't it? Because sine is bounded between -1 and 1. If we square that, then that's got to be smaller than 1. That I can say, I'm not sure if I'm with you, because I agree with this, but see this right here, if I take the limit of this, it goes to 1, and I need to squeeze between the same number. I need that to be a 0 and that to be a 0. What I'm trying to see, I'm telling you this is true, but I'm trying to get someone to convince me and everyone why this is true. Go ahead.
The sign of 0 is 0, so 0 is what is 0.
Yeah, I agree that if you plug 0 in here that you're going to get 0 and that's going to go to 0. I agree with that, but I'm saying why can I write that this is smaller than that? Why is that a true statement, that this is smaller than this? One idea was, well, this denominator's bigger than 1, and then I would agree, but it's not though. Not all the time. I gave you an example of a y and an x where it wouldn't be true, right? And then I hadn't even taken into account there's an x squared in front of it, right? Like that messes up things too. Yep.
Because sine creates a fraction, so even if it was divided by a smaller number, that fraction would be smaller, so sine's a great percentage.
Hold on a second, hold on. I want to make sure I'm addressing that. I'm not sure I'm convinced with that. Reorganize your thought.
So we know that both, if we take out sine squared y from, then we just make the fraction x squared, we consider the fraction x squared over x squared plus
Pause.
2y.
Pause. I think I know what you're saying. I think what you're saying is if we look at this and we don't think about the sine squared y so much, because they're the same in both of these, right?
Right.
Then continue.
Right. I came to the conclusion that x squared and y squared is always going to be a positive number, and because the denominator is x squared is a positive number plus a positive number, and it's dividing by one of those original numbers, it's always going to be less than or equal to 1, no matter what combination this.
What will be the whole ratio?
The whole ratio.
The whole ratio. Okay, so that's the key right here. This right here is less than 1, always. Do y'all see why? Pick an x, I don't care what it is. Whatever it is, these two are the same, right? And I'm adding more to this denominator now. This for sure is a positive number. So, well, it could be 0, couldn't it? But let's say if it was 0, then isn't this just a 1? And then these are exactly the same, aren't they? But if you pick any other, give me any x value, and then give me any y value that's not 0, this ratio must be smaller than 1. And if this is smaller than 1, then that times this would be smaller than 1 times that. Yes?
Shouldn't it be less than or equal to 1?
Yes, less than or equal. Yes?
Isn't it kind of easier to think of as like if you solve that inequality by like multiplying both sides by x squared plus 2y squared, and on one side you have x squared sine squared y less than or equal to x squared plus 2y squared sine squared y?
Okay, so
Like you multiply both sides of the inequality by x squared plus 2y squared. I mean, isn't that kind of like wouldn't solving the inequality that way kind of help you see it a little easier?
I don't know, does it help you see it?
I mean, for me,
Yeah, does that help you? I mean, because I could, if you wanted to do that, I could have just divided both sides by sine squared y, right? And then you're trying to just show that inequality and then multiply both sides by x squared plus y squared and then subtract x squared on both sides. And you get that, right? And that's always true. I agree with you, but what I think I want you to see more, or I think I'm trying to guide you as like what a Cal 3 student should try and see is that this is smaller than 1. Like you should be able to rationalize through that exercise without having to set up this inequality. That you should see that if these two are the same and I'm adding a positive number, then this must be smaller than or equal to 1. Now, if I change this to that, it's all over now. Because you have to be, this has to be something that you can guarantee is bigger than that. And if I take away the squared, then this could possibly be a negative number now. I need the squared there. So do you see how I'm thinking more about the number idea and like things being added as opposed to just getting to like a inequality sort of format. That's all. It's just a different way of thinking. You could do it that way. I saw another hand. Yes?
I was going to say, like, the problem with dividing by sine squared y is that you're no longer considering when y is equal to 0.
That's right. So you also have that consideration that if you take this off both sides, you're essentially dividing by it, and dividing by it means you're promising me it's never 0, and then you're eliminating the possibility that y could be 0. So there's problems, inherent problems with the inequality, messing with it like that. So,
Isn't that also
Yeah.
flip the inequality sign to divide across?
well, you wouldn't have to worry because you'd be dividing by a positive number because it's squared.
Oh, right.
So you only flip when it's negative. So here's where we are. we have the limit as xy goes to 0, 0 of 0 is less than or equal to the limit as xy approaches 0, 0 of the thing we were interested in. We didn't know what this limit was, right? But we were able to show that that's less than or equal to the limit as xy approaches 0, 0 of sine squared y, right? Because we believe this inequality to be true. Hopefully we believe that. I convinced you. And so now this, we take the limit, this goes to 0, which must be less than or equal to this, which is what we're looking for, but that must be less than or equal to this limit, and this is a straightforward Cal 1 limit. Let y go to 0, sine of 0, 0, 0 squared 0, so that approaches 0. So you've squeezed the answer you're looking for between two numbers that are the same. So our answer is 0. Doesn't matter the path. I don't have to check a path. All paths, guaranteed, are going to give you 0 as a limit. That's the only way to do it other than the path technique, which I just said you can't check every path. So this is about all we have in our toolbox to do limits of functions of two variables is the squeeze theorem. Yep?
Squeeze theorem only works with sines and cosines, doesn't it?
No. Any function that you can squeeze between two others, it'll work. The reason why sine and cosine, people always think squeeze theorem with sine and cosine is because that's normally when you see it, like when it's presented to you, they use those examples because you can always put sine between -1 and 1, right? Probably the first example you ever see with squeeze theorem, if you saw it in Cal 1, you may not have, is this one. You know, try to show that this limit, show that that limit is equal to 1, right? Show that that limit's equal to 1. Maybe not. Oh, sorry, it goes to infinity, sorry. This one. Show that that's 0. That's when you first see it in squeeze theorem, something like that. And so what you do is you do, okay, you start out by saying sine x is bounded between -1 and 1. And now what you do is you divide everything by x. And you don't have to worry about flipping inequalities because you're letting x go to infinity. So you're going to assume that's a positive number so that this doesn't flip. And then now you take the limit of that and the limit of that as x goes to infinity. You get 0 over 0, 0 and 0, and then that forces that to be 0. So most of the time when students see that squeeze theorem for the first time, it's something like that. So they start to associate squeeze theorem with trig functions, but it really can be anything. All right, we are done. Oh, wait, no, one last little note here. It's just a note. Continuity, right? Continuity. Well, we're just going to gloss over this, and I'm just going to give you the conclusion, which is all we need. And that is, when it comes to functions of several variables like f of x, y, all polynomial functions are continuous everywhere. Which means that when we look at that sheet that's floating in the wind, we should expect that there are no asymptotes, no holes, no jumps, breaks in the graph. If it's